Hi there, my name is Oshan, and I'm here today to talk to you about our project, which is the feasibility of using sensors and microcontrollers to detect aggressive behavior in the domestic environment. So to begin with, we went into this project with a couple of questions. Firstly, how do we quantify aggressive behavior? It's quite a broad subject. It's quite vague. It's quite sometimes open to interpretation. So how would we sort of boil that down to like a single particular metric? In this instance, we decided to focus on door slamming. Sort of, can we use our microcontrollers to detect if a door is being slammed somewhat aggressively, or if it's just being closed, sort of in a more ordinary fashion? Secondly, as well, given that these devices would be deployed in a home environment, potentially, we wanted to avoid just having sort of an open mic, just sort of sat in the room. That is, A, that's not very good for the privacy of the residents, and B, it's also pretty power intensive. Now, I'm not saying that door slamming is a definitive metric of domestic violence or aggressive behaviours. Families with children will certainly know that kids slam doors all the time, since most of us probably slam doors more than we realise, which is something I've certainly found since doing this project, that my neighbours must certainly despise me. So, with regards to sensors, we had two main options that came with our Arduino Nano BLE. So we had an internal IMU, so it's inertial measurement unit, so that includes accelerometer, gyroscope, magnetometer, or we had the onboard PDM microphone, so that essentially just detects whether or not there's any audio incoming. Now, we were quite wary of just using the microphone on its own, because we wanted to avoid having just a microphone open just 24/7, because not only is that impractical, it's also a huge concern for the privacy of the users. All we're really interested in is the door slamming. At the same time, we didn't necessarily want to just focus entirely on accelerometer data. Just because a door accelerates quite suddenly and then decelerates quite suddenly doesn't necessarily mean that a door has slammed, for example. However, in terms of what we'd actually use to classify whether or not a door's being slammed or not, we decided to go with audio as opposed to the accelerometer. So in order to train our model, what we needed was a large amount of data relating to sort of closing doors. So door slamming, door just closing normally, and on a variety of different kinds of door. However, we couldn't really find many of these that were publicly available. So what we did is we decided just to go ahead and make our own. Is we attached an Arduino to standard internal door. So we did that on a variety of internal doors of varying materials. We then used the Arduino to gather 2-second audio samples, both slamming the door and closing it normally, and then created our dataset sort of manually then. We decided on 2 seconds, somewhat experimentally, because we determined that was enough time to capture the full sound of closing the door without it being too lengthy and taking up too much memory. So we saved these 2-second samples as WAV files. Ordinarily, the device, if it was deployed, wouldn't just save these recordings, but for the purpose of the data collection, we just went ahead and did that. What we then did is we could then mix in sort of background noises on some of the samples, just to give it like a sense of extra randomness. The background noises we mixed in came from a Google dataset, sort of a variety of different background noises, so somebody doing the dishes, some white noise, traffic, exercise bike, that sort of thing. What we did is we just sort of then mixed these in at various relative volumes, relative to the volume of the initial sample. That way we can introduce a degree of randomness to some of the samples, and sort of artificially increase the size of the dataset without having to continuously slam more and more doors, which was proving somewhat unpopular with building management, as you can imagine. As part of our data processing, we took the WAV files and converted them into spectrograms using MEL filter bank energies. And what we found is actually quite interesting, is that there are very distinct signatures between the slam and the more sort of calm close. So even with background noise mixed in, we could still see a substantial difference between the two. and it was quite distinct when you look at it visually. So once we had our spectrograms, what we wanted to do then was feed this into a machine learning model of some sort in order to sort of classify the two. So we'd have our slams and we'd have our normal closes. The way we went around that is we went with a convolutional neural network in the end, since this seems to be the standard for when you're dealing with images such as the spectrograms. We've included a representation of the neural network here on the poster. So as you can see, it's a combination of convolutional layers, a couple of dropouts in there as well, that dense layer just before the output layer. So we've actually found that this is actually pretty accurate. Without any background noise, we're looking at an accuracy of around 88.89%. Once we mix in some background noise, obviously accuracy does decline, but it still only goes down to about 87.5, which is still fairly accurate. We then take this model and convert it down into TensorFlow Lite, and then further down again into Micro, because what that allows us to do then is we can actually run this on the edge. So the main advantage of having this done on the edge is latency. So say now if we wanted to do this on cloud, there'd be substantial overheads, as the data would have to go from the Arduino over the internet to the cloud, where inference could then be run, and then the result then sent back to the Arduino. But this way around, what we can do is we can run the inference on the Arduino itself and then just transmit that result to, say now, something like a Raspberry Pi or a mobile phone or some other kind of device nearby that can then store that outcome. Which brings us nicely on to our next point, which is how we think these should be deployed. So we would be looking at embedding the Arduino within the actual structure of the door itself. So most internal doors are hollow, so you could probably fit the Arduino quite nicely on the inside of the door. This both limits background noise and helps avoid any tampering. The only issue then is recharging the batteries, but that could easily be solved with wirelessly chargeable batteries that could be charged then through the door as and when needed. I'll now open the floor for any questions.